Electricity is often imagined as a kind of invisible fluid rushing through wires, pushed along by a battery the way water is pushed by a pump. This picture is so common that it feels almost unquestionable. Richard Feynman argued that this mental image, while convenient for simple explanations, creates a deep misunderstanding about what electricity actually is. Electricity is not a material substance that flows from one place to another. It is a pattern of interactions between charges, governed by electric fields that exist throughout space and respond almost instantly to changes in a circuit. To understand why the flowing substance idea is misleading, it helps to look closely at what is inside a metal wire. A wire is filled with atoms whose outer electrons are loosely bound and free to move. When a battery is connected, these electrons do begin to drift, but their motion is incredibly slow. Measurements and calculations show that the average drift speed of electrons in a household circuit is often less than a millimeter per second. At that speed, an electron would take minutes or even hours to travel a short distance along a wire. Yet, when a switch is flipped, a lamp lights up almost immediately. This simple fact already contradicts the idea that electricity works by electrons carrying energy from the battery to the bulb in real time. What actually changes when the switch is closed is the electric field throughout the circuit. The battery creates a separation of charge, producing an electric field that extends along the wires and into the surrounding space. This field establishes itself at a speed close to that of light. The electrons already present in the wire respond to this field by rearranging slightly, beginning their slow drift, but the energy that powers the bulb is guided by the field, not transported by individual electrons traveling long distances. Feynman emphasized that electric fields are not just mathematical tools or abstract ideas. They are physically real in the sense that they determine how charges move and how energy is transferred. When the field changes, charges respond. When charges move, fields change in return. Electricity, in this view, is a consistent interaction between charges and fields, not a stream of particles carrying power like trucks on a highway. The water analogy fails most clearly when we consider speed. If electricity were a flowing substance like water, then turning on a light would require that substance to travel from the power source to the device. But in reality, the response is nearly instantaneous, even over long distances. This makes sense only if the energy transfer happens through a field that already fills the space of the circuit. The wire does not deliver electricity the way a pipe delivers water. It shapes and guides the electric field that carries energy. Another reason the substance picture is misleading is that it hides the role of space around the wire. In the flowing, fluid model, everything important seems to happen inside the conductor. Feynman pointed out that this is false. The electric field exists both inside and outside the wire, and the energy flow can be described as moving through the surrounding space. The wire's job is to constrain and direct this flow, much like riverbanks guide water without themselves being the water. When engineers analyze circuits at a deeper level, especially at high frequencies or in fast electronics, the field-based picture becomes essential. Signals do not simply move through wires. They propagate as changes in electromagnetic fields along transmission lines. The shape, spacing, and environment of the conductors all matter because they affect the fields. This is why circuit layout is crucial in modern electronics, and why long cables must be treated as distributed systems rather than simple connections. Feynman also highlighted that thinking of electricity as a substance encourages incorrect questions. People ask where electricity is used up, or whether it gets stored, in wires. In reality, energy is transferred from one part of the system to another, often converted into light, heat, or motion, but the electric field itself is not consumed. The charges remain. What changes is their configuration and the energy associated with the field. Even the word current contributes to the confusion. It suggests a flowing thing, yet electric current is simply a measure of how much charge passes a point per unit time. It does not describe the transport of energy directly. Energy flow is described by the interaction of electric and magnetic fields, a concept that becomes clear only when we abandon the substance metaphor. By reframing electricity as a system of interactions governed by fields, Feynman encouraged a more accurate and powerful understanding. This perspective explains why electrical effects propagate so quickly, why circuit geometry matters, and why energy transfer does not depend on fast, moving electrons. It also connects electricity naturally to magnetism, since changing electric fields create magnetic fields and vice versa. Together, they form a unified description of how energy and information move through space. The misconception of electricity as a flowing substance persists because it works well enough for simple problems and everyday language. But Feynman believed that real understanding begins when we recognize the limits of our analogies. Electricity is not something that flows like water. It is a dynamic pattern of forces and fields, instantly responsive, deeply connected to space itself, and far more subtle than any simple fluid picture can capture. The second keynote challenges one of the most persistent misunderstandings about electricity: the belief that electrons themselves are what carry energy through a circuit. Richard Feynman stressed that while electrons do move, their motion is not responsible for delivering energy from a source to a device. The real carrier of energy is the electromagnetic field, an invisible but physically real structure that exists in and around the circuit and responds almost instantly when conditions change. To grasp this idea, it is important to separate two concepts that are often mixed together: charge motion and energy transfer. Electrons are charges, and when they move, we describe that motion as electric current. But current alone does not tell us how energy flows. An electron drifting through a wire does not bring a packet of energy from the battery to the bulb, the way a delivery truck brings goods from a warehouse. In fact, most electrons in a circuit never leave the wire they started in, and many only oscillate slightly around fixed positions. The slow speed of electron drift is a crucial clue. In a typical household wire, electrons drift at speeds measured in fractions of a millimeter per second. This is astonishingly slow compared to the near-instant response of electrical devices. When a switch is flipped, the light turns on in less than a microsecond, even if the power source is kilometers away. If electrons themselves were responsible for carrying energy across that distance, the delay would be obvious. Since it is not, the energy must be traveling in another way. Feynman explained that the moment a circuit is completed, the electric field throughout the entire circuit changes. This change propagates at nearly the speed of light. The electric field already exists in space, but its configuration adjusts when the battery applies a voltage. This adjustment sets up conditions that allow energy to flow. The electrons respond locally to the field by drifting, but they are not the main actors in transporting energy over long distances. Energy flow in electromagnetism is described by the interaction of electric and magnetic fields. When an electric field exists and charges move, a magnetic field is created. The combination of these two fields determines how energy moves through space. This energy flow is not confined to the interior of the wire. It exists in the space around the conductor, guided by the geometry of the circuit. A striking consequence of this idea is that energy can flow through empty space, even though electrons cannot. In radio transmission, for example, energy is sent from a transmitter to a receiver through electromagnetic waves traveling through the air or vacuum. No electrons carry energy from the antenna to the receiver across that space. Instead, changing electric and magnetic fields propagate outward, transporting energy. Feynman emphasized that ordinary electrical circuits work on the same principle, just in a more constrained form. Even in a simple battery wire bulb system, most of the energy flows through the space surrounding the wire rather than through the metal itself. The wire's role is to shape and guide the electromagnetic field, ensuring that energy moves efficiently from the source to the load. If the wire is bent, twisted, or rerouted, the fields change accordingly, and so does the path of energy flow. This field-based view also explains why circuit design matters so much at high speeds. In fast digital electronics, signals change extremely quickly. Engineers cannot treat wires as simple connections anymore. Instead, they must consider them as transmission lines where electromagnetic fields propagate along specific paths. The spacing between conductors, the materials around them, and even nearby objects affect how energy and information move. None of this can be explained if energy is thought of as riding on electrons alone. Feynman often used simple but powerful reasoning to make this point clear. If energy were carried by electrons, then removing the wire and replacing it with empty space would stop energy transfer completely. But we know that electromagnetic waves can carry energy through space. The only difference in a circuit is that the wire confines and directs these waves. The underlying mechanism is the same. Another important insight is that electrons themselves do not gain much energy as they drift. In a steady circuit, electrons move slowly and collide frequently with atoms in the wire, losing energy as heat. The energy converted into light or motion in a device does not come from electrons arriving with stored energy. Instead, it comes from the continuous transfer of energy through the electromagnetic field, which delivers power to the device as long as the field configuration is maintained. This understanding also resolves confusion about where energy is stored in a circuit. People often imagine energy piling up inside electrons or sitting inside the battery waiting to be released. In reality, energy is stored in the electric and magnetic fields. A charged capacitor stores energy in the electric field between its plates. An inductor stores energy in the magnetic field around its coil. These are not abstract bookkeeping devices. They are real physical stores of energy distributed in space. Feynman's insistence on the field as the true carrier of energy was not just a technical correction. It was a philosophical lesson about how nature works. Fields are not secondary effects or convenient descriptions. They are fundamental components of physical reality. Ignoring them leads to incorrect intuitions and flawed explanations, especially as we move beyond simple, slow circuits. The misconception that electrons carry energy persists because it feels concrete and intuitive. Electrons are particles. We can imagine them moving and transporting things. Fields, by contrast, seem invisible and abstract, but Feynman reminded his audience that nature does not care about human comfort with mental pictures. The correct explanation is often less intuitive but more powerful. Once this idea is accepted, many puzzling aspects of electricity become clear. The speed of electrical signals the importance of circuit layout, the behavior of alternating current, and the connection between electricity and light all make sense when energy flow is attributed to electromagnetic fields. Electricity stops being a mysterious fluid and becomes a dynamic interaction between charges and fields that fills space and moves energy with remarkable efficiency. In emphasizing that electrons are not the true carriers of energy, Feynman was guiding learners away from a misleading shortcut and toward a deeper understanding. The electrons matter, but mainly as participants that respond to and help shape the fields. The real story of energy transfer in electricity is written in the language of fields, spreading through space, shaping technology, and revealing a far more elegant picture of how the physical world operates. The third keynote focuses on a deceptively simple picture that almost everyone learns early on: a battery connected to a wire and a bulb, where electricity is imagined as leaving the battery, traveling through the wire, and being used up by the bulb. Richard Feynman argued that this picture, although useful at a very basic level, hides the most important physics behind how electricity actually behaves, especially when it comes to speed, cause, and the role of the entire circuit as a single system. When a battery is connected to a bulb, many people imagine that electrons start moving from the battery toward the bulb, and once they arrive, the bulb lights up. This creates the impression of a time delay that depends on how fast electrons move, but in reality, the bulb lights almost instantly after the circuit is completed. The reason is not that electrons suddenly become incredibly fast, but that the entire circuit responds as one connected system through the electric field. Feynman emphasized that a circuit is not a one-way path but a closed loop. The battery does not send electricity outward in isolation. It establishes conditions throughout the whole loop at once. The moment the switch is closed, charges redistribute everywhere along the circuit, from the battery terminals to the bulb filament and back again. This redistribution happens at nearly the speed of light, governed by the propagation of electric field changes, not by the slow drift of electrons. The battery's role is often misunderstood. It is commonly thought of as a container full of electricity that pours charge into the wire. In reality, the battery acts more like a device that maintains a difference in electric potential between its terminals. Chemical reactions inside the battery rearrange charges, creating an electric field in the external circuit. The battery does not supply electrons to the wire in any meaningful sense. The wire already contains vast numbers of electrons. The battery simply pushes on them by setting up an electric field. This distinction becomes clearer when we consider that electrons flow continuously around a circuit. They do not pile up inside the bulb or disappear after producing light. The same electrons that are in the wire before the circuit is closed are the ones that drift when the circuit operates. Energy is transferred, but charge is conserved. The bulb does not consume electrons. It converts electrical energy into light and heat through interactions inside its filament. The oversimplified battery wire bulb picture also hides the importance of the circuit's geometry. In the simple diagram, wires are often drawn as ideal, invisible connections with no influence of their own. Feynman pointed out that the physical arrangement of the wires matters because it affects how electric and magnetic fields are distributed in space. Bend the wires, separate them, or bring them close together, and you change the fields. This, in turn, changes how energy flows and how quickly signals propagate. At low frequencies and short distances, these effects may be small enough to ignore, which is why the simple picture works in basic education. But as soon as we deal with fast signals, long cables, or high-frequency currents, the limitations of the simple model become obvious. Signals can reflect, interfere, or distort depending on the layout of the circuit. None of this makes sense if we imagine electricity as merely flowing through ideal wires like water through pipes. Feynman often highlighted how the speed of electrical effects reveals the inadequacy of the simple picture. If electrons had to travel from the battery to the bulb before anything happened, there would be noticeable delays, especially over long distances. Yet, electrical systems operate with astonishing speed. Power grids respond almost instantly, and electronic devices function at frequencies of billions of cycles per second. This is possible only because what propagates quickly is the electromagnetic field, not the electrons themselves. Another hidden aspect of the simple model is the role of the surrounding environment. The battery wire bulb diagram usually ignores the space around the circuit, treating it as empty and irrelevant. In reality, that space is essential. The electric field extends into the surrounding air or vacuum, and the magnetic field wraps around the current, carrying wires. Energy flows through this surrounding space, guided by the conductors but not confined to them. This becomes especially clear when considering what happens if the wires are removed and replaced with antennas. The same battery-driven oscillations that once powered a bulb can now radiate energy outward as electromagnetic waves. The difference between a circuit and an antenna is not the presence or absence of electricity, but how the fields are allowed to spread into space. The simple picture of electricity flowing inside wires fails completely in this context. Feynman's critique of the basic battery wire bulb explanation was not meant to discard it entirely, but to show its limits. He believed that teaching simplified models without clearly stating their limitations creates confusion later. Students grow attached to the idea that electricity is something that flows and gets used up, and they struggle to replace this idea with a more accurate field-based understanding. A more realistic picture sees the circuit as a dynamic system in which the battery establishes an electric field, charges respond locally, and energy flows through electromagnetic fields distributed in space. The bulb lights because energy is delivered to it continuously by these fields, not because electrons arrive carrying energy from the battery. By revealing what the simple picture hides, Feynman encouraged deeper thinking about cause and effect in physical systems. Electricity is not a one-way delivery process, but a coordinated interaction across an entire loop. The cause, the response, and the energy transfer are all tied together through fields that respond nearly instantaneously. Understanding this changes how we think about electrical systems at every level, from household wiring to modern electronics and communication technology. It removes the mystery of instant response, explains the importance of circuit design, and connects everyday electricity to the broader theory of electromagnetism. What seems at first like a simple correction becomes a doorway to a much richer and more accurate understanding of how nature moves energy and information through space. Richard Feynman's final emphasis ties all the misconceptions together into a single lesson about how electricity should be understood, not as a set of isolated facts or mechanical analogies, but as a story of cause and effect governed by physical laws. Asking, and the what LEMO actually ED on without C, ROUUBLESES electrical phenomena, and how those causes spread through space and time. One of the most powerful ideas Feynman stressed is that electrical effects are never local in the simple sense we imagine. When something changes in a circuit, that change influences the entire system. Closing a switch does not merely affect the wire near the switch. it alters the electric field everywhere along the circuit. This change propagates outward at a finite speed, close to the speed of light, carrying information about the new conditions. The behavior of every component depends on this shared field, not on a delayed arrival of moving charges. This way of thinking replaces the idea of electricity as a thing with electricity as a process. A process has steps, timing, and relationships between causes and effects. When a battery maintains a voltage, it is constantly doing work to keep charges separated. When a current flows, it is not because electrons want to move, but because the electric field pushes them. When energy is delivered to a device, it is because the field configuration allows energy to flow into that device and be converted into another form. Feynman often pointed out that asking the right questions is more important than memorizing the right answers. Instead of asking how fast electrons move, he encouraged asking how fast the influence of the battery spreads through the circuit. Instead of asking where electricity is stored, he suggested asking where energy resides and how it moves. These questions naturally lead to fields, because fields are the only entities that can explain both the speed and the continuity of electrical effects. Another key aspect of cause and effect in electricity is the inseparable link between electric and magnetic phenomena. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. This mutual relationship ensures that disturbances can propagate through space even without charges present. Light itself is an electromagnetic wave, a self-sustaining oscillation of electric and magnetic fields. Feynman emphasized that everyday electricity and light are not separate mysteries, but expressions of the same underlying principles. This realization dissolves many artificial boundaries. The electricity that powers a light bulb and the light that emerges from it are connected by the same theory. The signals in a wire and the radio waves in the air follow the same laws. When people think of electricity as a substance, these connections seem accidental or confusing. When electricity is understood as field dynamics, the unity becomes obvious. Feynman also addressed the human tendency to cling to familiar images even after they stop being useful. The water flow analogy, the idea of electrons carrying energy, and the picture of electricity being used up all survive because they feel concrete. Fields, by contrast, are invisible and abstract. But Feynman reminded audiences that invisibility does not imply unreality. Gravity is invisible, yet its effects are undeniable. Electric and magnetic fields are just as real in their consequences. Understanding electricity as a network of causes and effects also has practical importance. It explains why shielding works, why grounding matters, and why electromagnetic interference can affect sensitive equipment. These phenomena cannot be explained by imagining electricity confined neatly inside wires. They only make sense when we recognize that fields extend into space and interact with their surroundings. This perspective also clarifies why electrical laws have the form they do. Ohm's law, Kirchhoff's rules, and other circuit laws are not fundamental truths carved into nature. They are approximations that work under certain conditions. They emerge from the more fundamental laws governing fields and charges. Feynman believed that appreciating this hierarchy of ideas helps prevent confusion when those simple laws fail, such as in high frequency or high power situations. At a deeper level, Feynman's approach reflects a philosophy of science. He believed that understanding means being able to explain why things happen, not just predicting outcomes. Electricity, when reduced to formulas and analogies without physical insight, becomes a collection of rules to memorize. When understood through cause and effect, it becomes a coherent story about how nature responds to change. This story also highlights the importance of humility in science. Even concepts that feel obvious can be wrong or incomplete. The history of electricity is full of revisions, from early fluid models to the modern field theory. Feynman used these examples to show that science advances by questioning its own explanations and replacing them with better ones when evidence demands it. By insisting on a cause and defect understanding, Feynman was not making electricity more complicated for its own sake. He was making it more honest. The universe does not simplify itself to match human intuition. It follows its own rules, and our job is to discover them, even when they challenge comfortable mental pictures. In the end, Feynman's lesson about electricity is also a lesson about learning itself. True understanding comes from asking what is really happening, tracing causes through space and time, and being willing to abandon misleading images. Electricity is not a mysterious fluid, not a stream of energetic electrons, and not a simple one-way process. It is a dynamic, interconnected system of fields and charges, responding instantly and coherently to change. Seeing it this way does not just correct a misconception. It reveals the elegance and unity of the physical world.